Welcome to another deep dive into the world of large language models.
Oh, yeah.
Today we're taking a look at the Byte Latent Transformer,
Interesting.
or BLT.
Mm-hmm.
This new architecture proposes to understand the nuances of text, everything from slang and emojis, even code, in a way that current LLMs just struggle with.
Yeah.
What's particularly exciting is that it achieves this without needing to be explicitly taught these nuances.
Yeah. What's really groundbreaking about BLT is its approach to a long-standing challenge in the field. And that is tokenization.
Right.
You see, traditional LLMs are trained on these tokens, which are essentially just chunks of text.
Yeah.
But this reliance on these predefined tokens has inherent limitations.
Yeah, it's like trying to understand a complex machine.
Right.
By just looking at its individual parts without seeing how they fit together.
Exactly. And that's where BLT diverges. It ditches the traditional tokenizer altogether and dives straight into the raw data of bytes. By learning directly from bytes, the most fundamental building blocks of digital information, BLT develops a more holistic understanding of the text.
It sounds like a pretty radical departure from the norm. What are some of the specific limitations of tokenization that BLT aims to address?
Well, the paper highlights several key issues. For instance, tokenization methods are often very domain-specific. A model trained on formal text might struggle with the casual language and emojis that are prevalent in social media.
So you're saying a model trained on academic papers might be baffled by a tweet.
Precisely. Another issue is vulnerability to noise. Even a small typo can significantly impact a token-based model's understanding of a sentence. And this problem becomes even more pronounced with multilingual text. Tokenization methods that are developed for English might not be effective for languages with different structures, leading to what the paper calls multilingual inequity.
It seems like tokenization, while a convenient tool, creates a sort of artificial barrier between the model and the true essence of language.
That's a great way to put it. BLT aims to break down that barrier by operating directly on the byte level, and the paper argues that this leads to several advantages, including increased efficiency, robustness, and adaptability.
Let's unpack how BLT accomplishes this. The paper mentions something called dynamic patching. How does this differ from traditional tokenization?
So instead of using a fixed vocabulary of tokens, BLT dynamically groups bytes into these patches. These patches are similar to tokens in that they represent segments of text. However, their size isn't predetermined. BLT employs a small separate language model to analyze the incoming byte stream and to predict the complexity of the upcoming bytes. Or complex sections, like those containing technical jargon or code, are grouped into larger patches. Simpler sections get smaller patches.
So BLT intelligently allocates its computational resources based on the complexity of the text. It's like a detective dedicating more manpower to a convoluted case compared to a straightforward one.
That's an excellent analogy. This dynamic approach allows BLT to be incredibly efficient and precise in its analysis.
Now let's delve into the architecture of BLT itself. The paper describes three core components. A local encoder, a latent global transformer, and a local decoder. Can you walk us through how these components work together?
Imagine a pipeline where the raw byte data flows through these three components. The local encoder is responsible for grouping the bytes into those dynamic patches we talked about. It uses a technique called hash-n-gram embeddings, which allows it to efficiently capture information about sequences of bytes without needing a massive vocabulary.
This hash-n-gram embedding sounds intriguing.
It is.
Can you elaborate on how it works?
Sure. So instead of storing every possible sequence of bytes, which would be incredibly inefficient, the local encoder uses a hash function to map them to a smaller set of embeddings. Think of it like creating a unique fingerprint for each sequence of bytes. This fingerprint or embedding then represents that sequence within the model.
Okay.
It's a clever way to maintain efficiency while still capturing a rich representation of the byte sequences.
So it's like a compressed representation of the data that still retains the essential information.
Exactly. Once the bytes have been transformed into these dynamic patches, they are passed on to the heart of the model, the latent global transformer.
And what does the latent global transformer do?
This is where the magic happens. The global transformer is a powerful neural network that analyzes the relationships between the patches, effectively learning the underlying structure and meaning of the text.
So it's like piecing together a puzzle where each patch is a piece. And the global transformer figures out how they all fit together.
That's a good way to visualize it. Finally, once the global transformer has processed the information, it passes it to the local decoder.
And the decoder's role is to...
The local decoder takes the processed information from the global transformer and translates it back into a sequence of bytes, giving you the output. Think of it as converting the model's understanding of the text back into a format that humans can read.
So the entire process is like a complex dance between these three components, encoding, processing, and decoding.
Exactly. And by working together seamlessly, these components allow BLT to achieve a level of understanding and efficiency that surpasses traditional token-based models.
This is all very impressive, but I'm curious about the practical implications. How does BLT's unique architecture translate into actual performance gains?
That's what we'll explore next. The paper provides some really compelling evidence that this byte-level approach offers significant advantages in terms of performance and scalability. But before we dive into those details, let's take a closer look at how BLT actually implements this hash enagram embedding technique.
Let's unpack the mathematics behind this clever approach.
Imagine a sequence of no bytes where no dollars can vary. We denote this sequence as $, B2, brand BN dollar. Now, to create a hash enagram embedding, we first convert each byte into its corresponding integer representation.
So if we have a byte representing the letter A, we convert it to its ASCII code.
Exactly. It's 65.
Precisely, once we have the integer representation of each byte, we apply a hash function to each enagram within the sequence.
And an enagram is simply a contiguous sequence of number items. Of a given sequence.
So, for instance, if we have the byte sequence representing hello, and we choose identical to 2, our 2 grams would be he, l, low. We then apply a hash function to each of these 2 grams.
What kind of hash function is typically used?
The paper mentions using a rolling hash function, which is particularly efficient for this task. A rolling hash function allows us to compute the hash of the next enagram by simply updating the hash of the previous enagram. This avoids having to recompute the hash of the entire enagram each time, saving significant computation.
That makes sense.
So we apply this rolling hash function to each enagram, but then how do these hashed values become embeddings?
Each hashed value is used as an index into a table of embeddings. This table is essentially a matrix where each row represents a unique embedding vector. So the hashed value of a particular enagram points to a specific row in this matrix, and that row represents the embedding for that enagram.
So we're not actually storing the engram itself, it's hashed representation, which points to a corresponding embedding.
And this is what makes this technique so efficient. It allows us to represent a vast number of possible engrams with a relatively small embedding table.
It's like a highly compressed dictionary where the hash values act as keys to look up the actual meanings, or in this case, the embeddings.
That's a great analogy. And the beauty of this approach is that it naturally captures information about the order of the bytes within the engram.
Because each engram, even if it contains the same bytes, will have a unique hash value, depending on the order of the bytes.
Precisely, this sensitivity to order is crucial for language understanding, as the meaning of a word or phrase can completely change depending on the arrangement of its constituent bytes.
This hash engram embedding technique is a brilliant solution to the challenges of representing a vast amount of information efficiently. It's like a secret code that unlocks the power of byte-level understanding.
And this is just one of the many innovations that make BLT such a groundbreaking development in the field of large language models.
Now that we've got a good grasp on the mechanics of BLT, especially that fascinating hash-n-gram embedding technique, I'm eager to hear how this all translates to actual performance improvements.
Well, the researchers conducted a series of rigorous experiments to evaluate BLT's capabilities.
Okay.
One area where BLT really shines is in its robustness to noise.
Okay.
They introduced various types of character-level noise into a standard language modeling benchmark called HeliSwag.
What kind of noise are we talking about here? Just typos?
They went beyond simple typos, exploring scenarios like converting text to all uppercase, randomly deleting or repeating characters, and even simulating internet slang with haphazard capitalization. You know, like, this is what IT would look like.
Ah, the language of the internet. Yeah. Certainly a challenge for any language model.
Indeed, and the results were quite striking.
Yeah.
BLT consistently outperformed a comparable Llama 3 model trained on the same amount of data.
Interesting.
What's even more impressive is that in some cases, BLT even surpassed the performance of a much larger Llama 3 model trained on significantly more data.
So it's not just that BLT is less sensitive to noise. It seems to have a deeper understanding of the underlying structure of language, allowing it to navigate these distorted inputs more effectively.
That's a key takeaway here.
Yeah.
By learning from bytes, BLT seems to develop a more granular understanding of language, recognizing patterns and relationships at the character level that token-based models might miss.
It's like BLT has a more innate sense of how language works, whereas token-based models rely on a more surface-level symbolic representation.
Precisely. And this deeper understanding becomes even more apparent when we look at how BLT handles phonetics, the study of speech sounds.
Right.
They evaluated its performance on a grapheme-to-phone task where the model has to convert written words into their phonetic transcriptions.
For example, taking the word cat and transcribing it as keet.
Exactly. And once again, BLT outshone the token-based Llama 3 model.
Okay.
This suggests that it's not just comprehending the written form of words, but also developing an awareness of their pronunciation.
That's fascinating. It's as if BLT is building a multidimensional representation of language, encompassing both its written and spoken forms.
It's a compelling observation, and it aligns with their findings on a benchmark called CUTE, which stands for Measuring LLM's Understanding of Their Tokens.
CUTE. Tell me more about this intriguing acronym.
CUTE is specifically designed to assess how well LLMs understand their own tokens, throwing some rather tricky challenges their way. These include tasks like swapping characters within a word, substituting characters, deleting or inserting characters, and even assessing semantic and orthographic similarity.
So it's like a comprehensive exam for character-level understanding.
Precisely. And BLT passed with flying colors, significantly outperforming the Llama 3 models, particularly on the character manipulation tasks.
Wow.
On some of these, it achieved near-perfect accuracy.
So BLT is clearly a multi-talented model, excelling across a range of tasks that demand a nuanced understanding of language at the byte level. It's not just about efficiency, it's about a more fundamental shift in how these models approach language.
Absolutely, and as we alluded to earlier, this shift also brings significant scaling advantages.
You're referring to how BLT can increase its patch size as the model grows larger without incurring additional computational costs.
Yes. To demonstrate this, they conducted what they call a fixed inference scaling study. They took a couple of token-based models and found flop-equivalent BLT models with larger average patch sizes.
For those of us who aren't deeply immersed in the world of computational complexity, could you explain what flop-equivalent means?
Of course, FLOP stands for floating point operations, which are essentially the basic mathematical operations that a computer performs.
Right.
So FLOP equivalent means that they use the same computational budget, but allocated it differently.
Okay.
The BLT models, with their ability to adjust patch size, could use larger patches, reducing the number of steps required by the global transformer.
And that saved computational power could then be used to increase the size of the model itself, leading to better performance, without increasing the overall cost. It's like optimizing a recipe to get more flavor out of fewer ingredients.
Exactly. And the results of this study were remarkable.
Okay.
The BLT models consistently outperformed the token-based models, even those trained on significantly more data.
Interesting.
It highlights the power of dynamic patching and byte-level understanding.
Yeah.
It's a more efficient use of computational resources, leading to both larger models and better performance.
This is a truly compelling argument for the potential of BLT. It challenges the conventional wisdom that bigger models always require more computational power. It seems that by being smarter about how we process information, we can achieve remarkable gains in both performance and efficiency.
Indeed. It's a testament to the ingenuity of the researchers behind BLT.
Yeah.
They've identified a fundamental bottleneck in traditional LLM design and proposed an elegant and effective solution.
And they didn't stop there. The paper also mentions something about byteifying an existing llama 3.1 model. What exactly does that entail?
This is where things get even more intriguing.
Okay.
They took a pre-trained llama 3.1 model, which had already learned a great deal about language from its token-based training, and transferred that knowledge to a BLT model.
So they didn't train BLT from scratch.
Yeah.
They gave it a head start using the llama model's existing knowledge.
Precisely. They initialized the global transformer of BLT with the weights from llama 3.1, keeping those weights frozen during training. This approach allowed BLT to leverage the language understanding of the llama model while still benefiting from the byte-level architecture. It's like taking a seasoned athlete and introducing them to a new, more effective training regimen.
And what were the results of this byteification experiment?
The results were incredibly encouraging.
Yep.
This byteified BLT model surpassed the performance of both a standard Llama 3 model and a BLT model trained from scratch on the same data.
Wow.
This suggests that byteification could be a viable way to upgrade existing LLMs, imbuing them with the advantages of BLT without having to retrain them from the ground up.
This opens up exciting possibilities. We could potentially enhance the capabilities of a whole generation of LLMs without requiring massive computational resources for retraining. It's like a software update for language models, unlocking new levels of performance and efficiency.
It's a remarkable finding that speaks to the versatility and potential of BLT.
Yeah.
It's not just a novel architecture. It's a new way of thinking about how we build and train language models.
This deep dive has been a revelation. BLT is clearly a paradigm shift in the world of LLMs. It challenges fundamental assumptions about how these models should be designed and trained, paving the way for more efficient, robust, and adaptable language understanding.
It's a testament to the power of innovation and the importance of questioning established paradigms. The researchers behind BLT didn't just incrementally improve existing models, they reimagined the very foundation of language modeling.
And the implications of this shift are profound. The paper hints at the possibility of developing truly universal language models capable of understanding any form of digital information, from text and code to images and audio.
Imagine a model that can fluidly navigate the diverse landscape of the digital world, seamlessly translating between different modalities of information. A model that can truly speak the language of the digital age.
It's a tantalizing vision of the future, and BLT seems to be a significant step towards realizing that vision.
The journey has just begun.
Yeah.
The research is still in its early stages, but the possibilities are vast.
Right.
As we continue to explore the potential of BLT and other byte-level approaches, we may unlock new frontiers in artificial intelligence and revolutionize the way we interact with the digital world.
This byte-level revolution is really starting to capture my imagination. It's like we're witnessing a fundamental shift in how we think about language and how machines can learn to understand it.
It's a truly exciting time to be working in this field. The success of BLT, particularly its ability to leverage the knowledge of existing token-based models through byteification, suggests a pathway for a more evolutionary approach to LLM development.
It seems like DLT is not just about creating a new models from scratch, but about finding ways to enhance and upgrade the models we already have.
Exactly. And that's one of the things that makes this research so compelling. It offers practical solutions for improving the efficiency, robustness, and adaptability of existing LLMs.
One aspect of BLT that we haven't really explored in depth yet is its potential for handling multilingual text and low-resource languages. The paper mentions this as one of the key advantages of the byte-level approach, but I'm curious to hear more about the specifics.
It's an area where BLT holds great promise. Traditional tokenization methods often struggle with languages that have different structures or limited training data. They tend to be biased towards languages like English, which have been the focus of much of the research in natural language processing.
So a model trained on a massive data set of English text might not perform as well on a language like Swahili, which has a different grammatical structure and a smaller amount of available training data.
Precisely, and this is where the byte-level approach of BLT shines, by operating directly on the raw bytes. It bypasses the need for language-specific tokenization schemes. It's like learning the universal alphabet of digital information, which allows it to adapt to different languages more easily.
It's like having a universal translator that can decipher any language as long as it's encoded in bytes.
That's a great analogy, and the researchers tested this capability by evaluating BLT on a variety of multilingual benchmarks, including tasks like machine translation and cross-lingual information retrieval. The results were very encouraging, with BLT demonstrating strong performance across a range of languages, including those with limited training data.
So BLT is not just about improving the efficiency and robustness of language models. It's also about making them more inclusive and accessible to speakers of different languages.
It's a step towards a more equitable and representative world of language technology where language barriers are minimized and information can be shared freely across linguistic boundaries.
It's a vision that I find both inspiring and exciting now as we wrap up our deep dive into BLT. I'm wondering about the broader implications of this research. What does it tell us about the future of LLMs and the future of AI more broadly?
BLT represents a fundamental shift in how we think about building and training language models. It challenges the dominance of token-based approaches and opens up a new realm of possibilities for byte-level understanding.
It's a reminder that innovation often comes from questioning the status quo and exploring new paradigms.
Exactly. And the success of BLT suggests that we're only scratching the surface of what's possible with byte-level models. As we continue to explore this new frontier, we're likely to see even more impressive breakthroughs in language understanding and artificial intelligence.
This deep dive has been an incredible journey into the cutting edge of LLM research. We've learned about the limitations of tokenization, the elegance and efficiency of BLT's byte-level approach, and the potential for this technology to revolutionize the way we interact with the digital world.
It's been a pleasure sharing these insights with you as you continue your own exploration of AI and language models. Remember to stay curious, challenge assumptions, and embrace the power of innovation. The future of language technology is bright, and BLT is shining a light on the path forward.
Thank you for joining us on this deep dive into the fascinating world of the Byte Latent Transformer. We hope you've enjoyed the journey and that you'll continue to follow the exciting developments in this field.